Hi everybody, it's me again with a video. Again, I'm out of town, so thought I'd get Miss Graphis here. Everybody say hi to Miss Graphis, make her feel comfortable. So this is all the stuff we went through yesterday. Maybe just as a quick review, we can look at bottom-up and top-down processing just to make sure. Now if I were an English speaker and I wanted to learn Spanish, in your mind, which would it be? Would it be more top-down or more bottom-up processing? Spanish would definitely be more top-down because it shares an alphabet. We were talking yesterday about what language would be more bottom-up processing, and the languages we came up with often were languages with different alphabets, Russian, Greek, Arabic, Chinese, Japanese, things like that. So bottom-up is where you're dealing with something new that you can't really make guesses about. Top-down is where you're dealing with something that you're somewhat familiar with and you can make guesses about it. So that's a good review there. We talked about selective attention, about how we're often very good at selective attention, but we're not very good at paying attention to other things. The cocktail party effect is where we're very selective about what we hear, that we can pick something out of the noise. Then yesterday, we were good at picking something out of the noise. We watched the basketball players pass it back and forth, but you didn't notice the moonwalking bear. So you were good at paying attention to the thing that I asked you to pay attention to, but not those other things. That is inattentional blindness. And even this ad was for noticing bicyclists. So the idea would be they're trying to say if you're looking for bicyclists, you'll notice them. If you're not, you won't. I don't know if that's true, if that's proven by science, but we do know that in this video, if you weren't looking for the moonwalking bear, many of you didn't notice the moonwalking bear. Then we watched the color changing card trick. And you could see that they changed both shirts and the background and the tablecloth. And all of that was, you didn't notice, most of you, probably because you just weren't paying attention. You're used to making predictions about the world. And then fifth period, we might have to watch this later. Maybe it was fifth period. I don't think we got to this video or to this video, but we can do that if you remind me fifth period on Monday. They're both good videos, but they're short. Now we're going to talk about how stimulation, which is light, sound, vibrations in the air, chemicals in the air, become sensation. How do we convert the world into neural impulses in our brain, which our brain then decides how to process? So transduction is what occurs. We have receptors in our brain that transduce that information. And if you look at the root, trans means across and duct means lead. You might have a different word, but they basically mean the same thing. So we're leading the information, this information from outside the world, we're leading it across the threshold of our sensation. So it goes from the outside of our brain to the inside, and it is our receptors that lead this information across that barrier from outside of our head to the inside of our head. And for the receptors, there will be olfactory bulbs in our nose that pick up smell. There will be the eardrum, the tympanic membrane, and the cochlea that pick up the sound. There will be the retina in the back of our eye that picks up sight. So we're going to talk about those receptors coming up. And those receptors, and let's just think to make it easy, the retina in the back of our eye that gets the light, that transduces that information. It transforms electromagnetic waves that go into our eye that we were talking about yesterday, transforms that stimulus into a nerve impulse. So it's an electromagnetic wave when it's outside of our head, and it is now a neural impulse while it's inside of our head. And again, be writing all this stuff down. I just talked about transduce, what that means, to lead across. And if you know it's to lead across, then the question is, and what you might want to write down in your notes is, what is being led across and what are they being led across? It is leading the information outside of our head to going inside of our head. It is taking the information that is in the world and putting it into our brain. So receptors transduce the stuff from outside of the world, outside of the brain into the inside of the brain. We'll review that again, but the idea is we have to have something. Another word, transduction, is conversion. Let's convert a chemical in the air to a smell in our brain. Let's convert a wave in the air to a sound in our head. So transduction is really conversion. So you might want to write that down in your notes too. Now we're going to look at thresholds, what we can perceive in the world. This is actually kind of interesting. In other words, what's the smallest impulse that we can hear? What's the smallest sight that we can see? And that's pretty interesting. When you start looking at this, you realize, wow, our senses are very, very fine-tuned. And I'm not trying to make a pun, but our senses are sensitive. We can really notice some crazy stuff. So if you look at vision, our absolute threshold for vision is if in a perfect world. Now, when I say in a perfect world, I mean there's no pollution in the air, there's no curvature of the earth. If we were just in, if we could find somehow a 30-foot, completely clear, completely dark space, we would be able to see a candle 30 miles away. So all it takes is a tiny, tiny, tiny bit of light for our eyes to see it. Oh, the other thing we would have to have is in order to be able to see that, our eyes have to not have seen light recently. You know how it is when it's really light and then we turn off the lights and you can kind of still see the lights and your eyes are not sensitive to the light. They say it takes about a half hour for your eyes to be completely ready for that darkness. So all this is pointing out that we have very, very acute vision that we can see a long ways away. And this is in perfect conditions. And also when we talk about absolute threshold, let me back up. What this says is in these perfect conditions, over half of the people given the vision, given the candle at 30 miles can see the candle. So you might want to put that in your notes. Absolute threshold is when, as soon as at least 50% can see it, then they call that the absolute threshold. So a candle at 30 miles away, half the people can see it, half the people can't see it. And the closer the candle gets, the more people can't see it. Sound. I wish we had a mechanical watch, and we've tried it in this room, but the problem is there's so much ambient sound in this room with the freeway and the construction outside and things like that. So if we were in a quiet room, a normal quiet room, and let's try it with my clock. We really can't do it. I have a ticking clock, but it won't work. So a mechanical watch with a second hand. Think of how tiny, how very quietly that clicks, that ticks. So in a perfect world, if we had all of the conditions right, if we had a perfectly quiet room, 20 feet away, and think of 20 feet, that's probably 7 to 8 full steps away. In a perfect world, somebody could walk 7 to 8 steps away, and if they held up their watch, we could hear it ticking 7 to 8 steps away. So our hearing is much more sensitive than we realize if we really pay attention and if we don't have all that noise pollution out there. Taste. So what they would do is they would say, how much, if I had 2 gallons of water, think of 2 gallons. 2 gallons, think of a gallon jug of milk, and then put 2 of them in there. So we put a half of a teaspoon. And when you think of a teaspoon, that's the small spoon that you have in your house. That's not the big spoon, that's the small spoon. So a half a teaspoon of sugar in 1 gallon of water, we would be able to tell that sugar was in there. So that's pretty dang sensitive. Half a teaspoon is not much. So our sense of taste is a lot more sensitive than we really think it is. The sense of smell. So you think of a 3-bedroom apartment, my guess would be about, that would be maybe 1,200 square feet, 1,400 square feet. So think of 3 bedrooms. Think of maybe the main floor of your house. If we put 1 drop of perfume in that house, in a perfect world, at least half of the people would be able to smell that perfume. So there's a lot of odors going around, and it's partially, I think, as we get older, we smell less, but partially as we're not paying attention. And think about what the absolute threshold would be for a dog. They say their smell is so much more sensitive than ours. That's pretty fascinating when you think about it. But even this, it's just in a perfect condition, we would be able to smell that. And that's, our senses are pretty sensitive. That's pretty crazy. And this one I love because it sounds like a haiku. The wing of a bee falling on your cheek from a distance of 1 centimeter. Now, no bees were harmed in the making of this PowerPoint, but just think of how thin of a tissue the wing of a bee is. It's just so tiny and so light. And if we dropped it just barely on top of your cheek, you'd be able to feel that. Now again, think back to the chapter we just looked at the homunculus. Your face will be able to sense a heck of a lot more than, say, your arm or your leg or your back would. So we know our face is a lot more sensitive, but our face, you see this? So sensitive. I mean, it's just a bit barely touching it, and we'll be able to sense that. So when you look at all this, in a perfect world, if we were in the perfect state, in a perfect environment, we would be able to sense a lot of stuff. Part of it is we're not paying attention. Part of it is we have light pollution. Part of it is we have air pollution. Part of it is we have sound pollution. But if we were exactly the way we should be, we would be able to sense a lot of stuff. So on this next slide, I just want to see if you notice anything. I'll read this aloud. I'm not trying to indoctrinate you. It's just something that some people know. The Lord is my shepherd, I shall not want. He maketh me to lie down in green pastures. He leadeth me beside the still waters. He restoreth my soul. He leadeth me in the paths of righteousness for his name's sake. Yea, though I walk through the valley of the shadow of death, I will fear no evil, for thou art with me. Thy rod and staff, they comfort me. Thou preparest a table for me in the presence of mine enemies. Thou anointest my head with oil, my cup runneth over. Surely goodness and mercy shall follow me all the days of my life. And I will dwell in the house of the Lord forever. You can't see the forever part below. I'm sorry about that. Did you notice anything? And I'll bet some of you did and some of you didn't. But what happened here is the font got a lot bigger as we went through. But what's interesting is you notice it got a little bigger each time. Now, if I switched from this to this, you might have noticed. But this is kind of like the cliche of the frog in boiling water that's getting turned up slowly doesn't notice the difference. So really what we're talking about here is the just noticeable difference. Maybe you noticed it right about here. Maybe there was too big of a jump. But what we have right here is if we switch from this to this, it would be noticeable. When we switch from this to this, probably not noticeable. So there are, not only is there an absolute threshold is what we either notice or we don't notice. This is when something changes, when there is a difference between two things, what do we notice? So we're going to talk about difference threshold, and that was with the Lord's Prayer. So the difference threshold, and we're going to talk about just noticeable difference of the difference threshold. Here's what I want you to write about in your notes and think about. Have you ever been in the car with a friend or your parents, and there's a song on? Yeah, I'll go this way. There's a song on that you don't like, and it's too loud and it's bugging you. And maybe you're driving and you have control of the volume on your steering wheel, and you're trying to turn down the volume very slowly, but you don't want people in the car to notice. Or vice versa, you're trying to turn it up and you don't want people to notice. What you're trying to do is you're trying to turn up the sound or turn down the sound so that the difference cannot be detected. You're trying to stay within the difference threshold. If you just cranked it, or if you just turned it down really low, you would be outside of the difference threshold. What we're trying to do is we're trying to stay within the difference threshold. How do we not let people notice? Kind of like, let's go back here, kind of like this. If we're turning it up just a little bit, we're staying within the difference threshold. If we go from here to here, that was too much of a change. And there were a couple of people who studied difference threshold, Weber and Fechner. And we're going to talk about both of those, and then we're going to watch a couple of videos. And I know it's going to be confusing. It's a Friday. Let's talk about it. Let's watch the videos, and then we'll review it on Monday. So Weber's law, or Weber, I've seen it pronounced that way too, says the just noticeable difference differs by a constant minimum percentage. And we're going to do the envelope experiment. We're going to steal from the, well, no, we're not going to steal. We're going to do this weight experiment. We're going to talk about this in the video, and we'll get there. But, so, what it's saying is, you can only, and I know some of you in here will never do that because you're much nicer than I am, but I used to steal from my parents' change jar. And I kind of could figure out how much I could steal without being noticed. And this is the same thing with weight. Let's say we're taking, well, it's hard because I want to show the video. So what I'm going to do is I want to just stay with this, and we only have 1 more minute on this video. So I know it's a little confusing, but it's saying the just noticeable difference in weight. If we increase weight, we can only increase weight by 2% or less for people not to notice. If we increase the weight of something, if we go over 2%, we're going to notice. So I know that's confusing. We're going to watch the video. We're going to review it on Monday. Don't worry about it. And then Fechner's law is very, very similar. It's saying that if you increase the strength of a stimulus, it will produce smaller increases in magnitude. So for instance, if you turn up the car stereo by 5 decibels at a low volume, you'll notice. If you turn it up from 50 to 55 decibels, you'll notice. But if you turn it up from 80 to 85 decibels, you won't notice. Here's another example. If you have a coffee with no sugar and then you put in a sugar, you'll notice. If you have a coffee with 8 sugars and then you put in 9 sugars, you probably won't notice the difference. And that's Fechner's law. So there's a video here we're going to watch. I'm going to have Miss Grafis take you there. I've got 4 seconds on the video. So Grafis will show you these 2 videos and then we're done. Have a good week.